I'm Dan Sweeney from MathSpec Incorporated. In this video, I will demonstrate how our Excel add-in can help identify an unknown compound from its accurate mass MSMS data by comparing the modular structures of the unknown compound to modular structures of a similar known compound. Carolyn Huber and her co-authors recently developed a novel high-throughput workflow for screening pesticides for human metabolites. The objective of their work was to develop a very useful workflow, not to perform structural elucidations of the numerous metabolites that were generated in their study. They have shared with MassBank many of the high-quality accurate mass MSMS data produced in their study. In this video, I will analyze the MSMS data of a metabolite of the fungicide fenpropimorph, MassBank HB002861. Huber et al. Had already determined that this metabolite had gained one oxygen atom relative to fenpropimorph. Our objective here is to determine where that extra oxygen was added to this compound. I have cut and pasted the mass intensity data from MassBank into a Microsoft WordPad document and saved this as a plain text file. I then imported this data set into Sheet 1 of Excel. In column A are the masses, and in column B is the intensity of the corresponding fragment ion. This is the formula of fenpropimorph itself. I'm going to calculate the mass difference between this precursor ion and the formula for the fungicide. It's going to equal A33 minus the mass of a proton and minus the mass of D33 15.995. If we look at the mass of oxygen, it's almost identical. So indeed, this metabolite of this fungicide is increased in mass relative to the fenpropimorph by the mass of an oxygen atom. So I'm going to click on the add-ins, and the little icon on the right side, if I click on that, that will bring up the worksheets that I need to produce modular structures. Let me expand this out. I'm going to copy the mass intensity columns. Into this is the data input worksheet. Paste that down. There was no MS full scan data to get the isotope pattern of the precursor ion. I could use the formula for the fungicide, which should be pretty close probably. Paste that in here, and then I can estimate the so this gives us an estimate of the isotope pattern. Okay. I'm going to leave fluorine at 0 I know that the metabolite's not going to have a fluorine in it. I don't know about whether there's odd electron subfragments, so I'll check that. The default parameters are fluorine 0, mass window error for all these fragments, and the protonated molecule 3 millidaltons, a 9%, so basically 22 plus or minus 9, 3 plus or minus 9. So it's a pretty wide window for the isotopes, and subfragment restriction means that if there's an unusual formula, it'll get weeded out, but only if we make this a number. 0 will not affect anything. So now I'm going to click on transform, and that will start the partitioning process. While that's running, I'm going to talk a little bit about what the Excel add-in is doing. Now, many of the MSMS fragments of a compound could be viewed as being composed of multiple subfragments or smaller pieces. So, for example, this one, this one, this one. We can obtain the masses of these smaller pieces, these subfragments, by simple additions and subtractions. For example, we have some of the neutralized fragment ions. There may also be simple differences and some mass differences. The Excel add-in checks for sets of masses that sum up to the mass of the precursor molecule. These are called subfragment masses. This operation is very CPU intensive. The subfragment masses are then converted into subformulas, and then possible spatial alignments are also assigned based on logic. Now, with this approach, we're not working backwards from a possible structure. There are no fragmentation rules involved. We're trying to answer the question, what might the structure look like that produced this MSMS spectrum? Okay, this is done. I can go back to the data input page. It took 32 seconds. And now we can look at partitions. The partitions are ranked from 1 to 6 based on the partition score. The partition score is how many fragment ions can be assigned to this partition, and it's also based on the intensity. So, for example, an intensity of 4 is not going to help the score very much. A 100 will help quite a bit. So actually partition 1 and partition 2 have the same partition score. And this one has 6. The maximum number of partitions that you can get, or maximum number of modular structures, is 6. The top graph it shows how relative sizes of these subfragments. So in this case, they're all, pretty good size. There's one small one, this water, or 18. Now I'm going to bring this up a little bit. So now we can see formulas. Now often there are, for each of these 5 masses, there may be more than one possible subformula. Now this says that it's a linear arrangement of these 5 subfragment formulas. If there's an arrow, a set of arrows out here, we can look and see other possible. Now here's the same, all connected to white, but 5 to 3. So this one has quite a few possible arrangements. If we look at this linear alignment, we can put this together as what I call a modular structure. So basically, these are the 5 subformulas arranged in a linear fashion. If we look at fenpropimorph, the compound can be analyzed the same way, and I found that partition 3 has a very similar set of masses and exactly the same formulas, except the subfragment 5, subformula 5, is C4H8O versus C4H8. So we can hypothesize that the C4H8 in our analyte has become a C4H8 with a oxygen on it. Now the number of hydrogens in the subfragments often differs from the number of hydrogens in the corresponding substructure. Other partitions may select a different set of bonds to disconnect. The actual molecular structure shown is in the mind's eye. We're seeing C7H6. Now we can imagine, based on the structure of fenpropimorph, that the other substructures have not changed, but we don't know that from the mass spectral data. So this approach assumes that the simplest explanation of the data is the most likely explanation. In conclusion, a change of one substructure of a molecule can often be localized by comparison of its modular structures to modular structures of a similar authentic sample.